So last time we used the limit process to find the exact area under the curve rather than just estimating the area under the curve with a finite number of rectangles. Instead, when we let the limit as n goes to infinity, what we say the limit of the Riemann sum, then we're finding the actual area. So we're not using 4 rectangles or 10 rectangles or 100 rectangles. We're letting those number of those rectangles go to infinity. And when we take the limit of that sum, that gives us the actual area under the curve. So last time we did a linear example, which was kind of nice. The algebra is a little bit nicer, but even kind of better is when we finished, we were able to verify it with just some basic geometry, which is always comforting. But now we're going to end this section with an example of a quadratic. So we have y equals 9 minus x squared on the closed interval from 1 to 3. And so that's going to be our second and final example here. So again, notice we're finding the actual area here. So the area equals, once you take the limit as n goes to infinity of the sum, then you're going to be finding the actual area. It's no longer an approximation of the area under the curve, it will be the actual area under the curve. All right, so limit as n goes to infinity of sum as I goes from 1 to n of f of c sub I. Well, my function here is 9 minus x squared. So now I need to look at my representation for my c sub I. So we're going to default to the easier representation of c sub I. So we are going to use, and you can see up above from the last video, we are going to use the right endpoints for our c sub I representation. So c sub I is equal to a plus I times delta x. So the a in this case is 1 plus I times, and our delta x in this case, b minus a, so 3 minus 1 over n. So what we have is that c sub I is going to equal 1 plus I times, and the delta x then is 2 over n. So this becomes 1 plus I times 2 over n, or 2 over ni, or 2i over n, or however you want to write that. And then times our delta x, and we just found delta x in our work over there on the right hand side. That was the 2 over n. So of course this right here, this was just the delta x. So it's the width times essentially the sum of all of the heights, where we're using the right endpoints for representation for our height. And remember what we talked about last time, it doesn't matter if we use right endpoints or left endpoints or midpoints or any point in the interval. Once we let n go to infinity, we will get to the actual area regardless. All right, so let's see what we can do with this. So again, I choose to bring my 2 over n in front of this entire sum because it does not have an index of I in it. So it can be treated like a constant brought in front of the sum, not in front of the limit. And so now we need to start to think about multiplying out this 1 plus this 2 over n times I. So 1 plus 2i over n, or 2 over n times I. So we're going to have to multiply that out. So let's go ahead and do that here. So we'd have 1, and then 2 over n times 1 plus another 2 over n times 1 would be 4 over n times 1. But I'll go ahead and write them. So we have a 2 over n I plus another 2 over n times I. And then the last term, 2 over n times 2 over n, and i's in both of those, is going to be 4 over n squared times I squared. Now we do need to be a little bit careful here. We've just replaced a product when we multiplied it out with a sum, so it's really 9 minus that whole quantity. And again, these two are like terms, so this really becomes 2 over ni plus 2 over ni. Add those up and you have 4 over ni. So here's what that binomial multiplied out becomes. And then we now have minus that quantity. So we're going to need to distribute that negative through to all three terms. So 9 minus 1 minus 4 over ni minus 4 over n squared I squared. Alright, so let's bring this back in here. I don't like to go too far without kind of rewriting where we were at. So this is the limit as n goes to infinity of 2 over n times the sum as I goes from 1 to n of, and we now have, the only simplifying I can really do here looks like just the 9 minus 1. So I can't do a whole lot of simplifying here. All right, and so now we are down to being able to apply our properties of sums, and take the sum term by term. So let's go ahead and take a look at that. So limit as n goes to infinity of 2 over n times the sum as I goes from 1 to n of 8 minus the sum as I goes from 1 to n of 4 over n times I minus the sum as I goes from 1 to n of 4 over n squared times I squared. All right, now we're going to apply kind of our final property of sums before we get to the sum formulas, which says in those last two sums that we have there, the 4 over n, like on this second one, can be brought in front of that particular sum as a constant multiple. It is a factor that does not have an I, so it is treated as a constant multiple. And same thing in the last sum, the 4 over n squared is a factor that does not have an I in it, so it can be brought as a factor in front of that sum. And now we get to apply our sum formulas from the beginning of this section. So the sum of a constant is that constant times n, and then minus 4 over n times the sum as I goes from 1 to n, the sum of I, that was our n times n plus 1 all over 2. And then the last term here, the 4 over n squared is the multiple. And the sum of the squares, if you remember that one, that was our n times n plus 1 times 2n plus 1 all over 6. So these sum formulas, these were at the beginning, if you remember, a number of videos ago. Oops, I did not mean to do that. Hold on just a second here. I'll erase that later. So if we, gosh darn it, sorry. If we go back, all I really wanted to do was kind of scroll back up here. And so here's where we were looking at, if you see these two sum formulas, these were the ones we were talking about right here in the middle of that first page. So that's really what we were looking at there. So let's bounce back. Here we go. Okay, so that's where those were. Continuing. You know, if you want, this is where you have a little bit of flexibility. You definitely must distribute through your 2 over n to all three terms here. And then it's up to you. Sometimes it's almost too tempting to not do some reducing of the n in the denominator with like the monomial n's that are in the numerator. But that is a little bit of the user's choice, I guess, on that. So in the first term, I would certainly have 16n over n. And that's probably one that's almost so tempting you can't resist reducing those n's. In the second term, I would have 4 times 2 would be 8 times the n plus 1 all over, in the denominator, n times 2, so the 2n squared. And in the third term, it looks like the 2 times the 4, I would have 8n, n plus 1, 2n plus 1, all over n squared times 6, so 6n cubed. Now, what we want to notice here as we take our limit term by term is really what we have in the first term. If you want to reduce n over n as a factor of 1, you can. The limit as n goes to infinity of a constant is just going to be that constant. Or you can think of how we'll kind of think of these next two terms is in this numerator. What we really have in the second term here is we have 8n squared. And I really just care about the leading term there, the term of highest degree, but you could distribute plus 8n over 2n squared. But what I really care most about is the fact that I have the degree of the numerator is equal to the degree of the denominator. And then let's kind of think about in the last term, sort of the same thing here. If I multiplied the 8n times the n, that would have been 8n squared. So it's kind of like thinking about how this would have been 8n squared plus 8n. You don't actually want to have to do this, but if you think about how that would work, and then you would multiply that by your 2n plus 1, what you really care is that the term of highest degree would have been 16n cubed. And then you don't really even care so much about the terms of lesser degree. You really just care that you have a degree 3 in the numerator and in the denominator there. So what we really have is going to then be our limit as n goes to infinity of 16 is just going to be 16. Let me first just rewrite this for completion. And then the limit as n goes to infinity when degree of numerator is degree of denominator. These limits reflected the rules for your horizontal asymptotes. And so this is the 8 divided by 2, or of course 4. And then the last term, degree of numerator is equal to degree of denominator again. And so this would have been, again, the ratio of the lead coefficients. So we really end up here with 16 minus 4 minus 8 thirds, or 2 2/3. So 12 minus 2 would be 10, minus another 2/3 would have been 9 and 1/3 square units. So that would have been our actual exact area under the parabola 9 minus x squared on the interval from 1 to 3.